Swayam Prabha. Digital India. Educated India.
Hello and welcome back. So in the last class I covered position sensors, especially optical sensors encoder which are of incremental in nature, as well as optical sensors which are absolute in nature, right? So today, continuing further, I will be discussing a special type of sensor which is very simple, that is potentiometers. That also can be used as a position sensor. So we'll be covering today, and we'll also see a Hall effect sensor that I initiated in my last lecture as magnetic sensor. Continuing further with that, today also I'll be using that Hall sensor as a position sensor, and velocity sensors I'll be talking about today. So yes, let us continue further. So let me just take you back to your high school when you have first encountered this type of sensors. Not as a sensor first, but as a simple Ohm's law you did this experiment maybe. So that is what is a potentiometer. I'll be using it today as a position sensor. Let me see if I can demonstrate you like that. So yes, let us continue. So hope you know what is voltage divider. So you very well remember this fundamental thing. So you have a voltage here, you have a resistance here, you have another resistance here, and this is your ground, right? You supply anything over here as an input. If at all I tell you this is resistance 1, this is resistance 2, so what is the voltage which is output here? So this can be quickly given as VO is equal to R2 by sum of both of these resistance R1 plus R2 into V input. Okay, so this is very straightforward. If R2 goes to 0, if R2 tends to 0, voltage output becomes 0. If R2 becomes equal to R1 plus R2, that is this point shifts to this end. So what do you see as an output is straight away exactly the voltage input. So this is the first principle I will be using to go to this type of sensor. So you see the arrangement is like this. Arrangement is very much like this, the way it is shown here. So you have a slider here. So this is your resistance strip. Okay, so this is your strip, okay, on which you have a pointer that continuously keeps in contact with that. This is this one. This is a sliding contact that slides over that. So here is the supply which is entering here, and this is your ground. The same circuit is here, which is implemented in a vertical way. Here it is shown as an horizontal one. So you see this can be compared with this, where R2 is a variable. Okay, R2 is a variable because this slider can move in this direction, okay, up and down. So this slider can touch this point which is 0 potential, or this slider can touch input potential. So anywhere in between it will give you some voltage as an output which is somewhere between 0 to V in, that is the supply voltage. Okay, so this is the first principle of this. Let us see how it is. So yes, this can be derived using the way it is shown here. So yes, here is the current that is entering from here. This is your current, it passes through, it goes here. The same current passes through whole of this line. So yes, the current can be taken up in two ways. First, it is equal to voltage input, that is the total voltage input, divided by total resistance, which is R. So this is the current which flows through this small resistance. Okay, and if you take in otherwise from here, so current is also equal to this voltage output, that is the voltage output, and this is R by L times of X. How it is? It is linearly proportional. If total is your resistance strip of total resistance R and total length L, I assume that this resistance is varying uniformly, resistivity is constant. So any place in between which is at a distance X, resistance from here to here will be given as resistance is equal to, for the strip is X by total length L into total resistance. So this is your resistance for this small strip which is covered here. Okay, so this is the resistance. So this goes here. I move ahead and just did some cross multiplication task from here to here. You see, so voltage output is equal to V in by R, R by L times of X. So if you strike off these two, so you are remaining with voltage output is equal to X by L times of voltage input. So this is the voltage input. So yes, so what do you see? Voltage input is constant, this is constant, total length of this strip is constant. So voltage output is equal to V in by L, that is a constant, times of X. So this is equal to, so the output voltage is proportional to displacement. So you see, output voltage is proportional to displacement. Let us say I have maximum voltage of 5 from here to here and total displacement is something around 100 mm of this strip. So you see, if I am somewhere in between, if I am tapping from somewhere in between, that is if this is 50 mm, okay, so voltage output will be 2.5 volt, got it? So if I am again further going here, that is 25 mm, my voltage output becomes 1.25 volts, okay. So that is the way. So voltage is linearly proportional to the displacement. So if it touches 0, output becomes 0. If it touches 100 mm, output is 5 volts. So 0 to 5 volt, 0 to 100 mm. So it is linearly proportional. So this is the way this sensor is designed. This is very simple, and yes, it can be used to measure your displacement. So it looks like this. It looks like this. I have one in my hand. It is a Gefran make. So yes, you see, it has a slider. It has a slider that can slide from here to here. Okay, that gives you an output. So it looks like this. It has 3 wires. You see, it has exactly 3 wires. So red one is for voltage input, ground is ground, and output is in the yellow wire. So it is a 3-wire system. It looks like this. So it is something around 200 mm maximum displacement I can make, that is 20 centimeter is the, and this is the mounting flange with which it can be mounted anywhere, and the wire goes out from something like this. So yes, so this is very simple. This is a linear slide, okay, and it can measure 0 to 200 mm, okay. So similar is the audio mixer. If you have seen, it is very similar. So it goes like, there are multiple sliders in your audio mixers. You must have seen if you have attended any music shows or anything. So they have multiple. You have microphone, you have piano, you have other instruments. Input from all of them, they come together and they are mixed using this. So you have something which is called as sliders, different sliders to control different volumes. So this is the way it is done. So exactly same instrument, same tool is used to mix different inputs, okay. So that is what, so in amplifiers it is used. Position sensors, yes, that is what it is meant over here. We are concerned more about this. And controllers, there are knobs, linear slides also, and as a velocity sensor also. I will tell you how it can be used as a velocity sensor towards the end of today's lecture when I will be covering this, okay. So yes, advantages, yes, you know, it is from your high school physics. It is very simple to understand. It is linear already. You don't need any additional circuit to linearize it. Voltage output can go from 0 to voltage input. So if you have to make this signal go to a long distance, this voltage can be as high as 24 volt, which is used in the industry. Doesn't require any kind of amplifier as such. They are very inexpensive because it is made up of just a slider and some enclosure to cover your resistance strip. Okay, so yes, disadvantages are definitely there. They are they have very poor life, because you know this slider is going to rub against your resistance slide. So with time it goes little noisy because you have some wearing that is happening. They are sensitive to dust and humidity. If you allow dust to get in, but the kind of potentiometer that I showed you, it is very nicely enclosed. So this doesn't allow dust to get in probably, so very less amount of dust can get in. Even a small amount of water sprays, they are very safe. So that can be taken care of, so it is very good. So dust and humidity they are sensitive to, because your resistance strip, if at all there is any moisture in between, so resistance will not be uniform, output will not be that reliable. Okay, but still this is very widely used as an absolute position sensor. Okay, now moving ahead in a similar way, if you are familiar with your audio amplifiers, even your radios, you remember this small device that is there as a volume control knob, bass, treble. So various inputs are there. They all use this kind of thing, which is known as a rotary potentiometer. Again, the principle is exactly the same. Okay, so you have an output. Here. So this is your resistance strip. Okay, one end of it you have voltage that is input here, other end is connected to ground. Okay, and at somewhere in between it is establishing contact, okay, from where you are tapping in and you are taking the output voltage. So system is almost the same, only thing is your resistance strip is arranged in a circular way. See how it works. This time this length x, the one that you had in your earlier scenario, yes, this was x. This time this x is straight away in a circular way, and this x is proportional to, if I write down, this x is proportional to angle. This radius is there, so x is equal to a times of theta, where theta is angle subtended by the wiper from the reference point, that is ground. So this is ground. So from here to here, that is the contact point, that is the angle which is subtended. So displacement x now is proportional to theta. Okay, the same equation now can be written as output voltage is equal to, instead of x by L, I can write a theta, so times of V input. So finally output voltage now is proportional to theta, because voltage input is constant, length of the total strip length is constant, a, that is radius of this, is constant. So overall output is proportional to theta. You got it? So now this tool now can be used as an angle sensor. So if theta is equal to 0 degree, output will be 0. If theta is equal to complete angle from, let us say this is 270 degree, okay, if it is 270 degree, it is output voltage is VCC, that is the supply voltage. So output voltage varies from 0 to the supply voltage. In industry it is 24 volt. So let us say if this is fitted in industry, so your output will go from 0 to 24 volt, right, for 0 to 270 degree. There are a bit of problem with these kind of thing. It cannot keep on running, you know. You cannot have continuous rotating potentiometers. There are few designs which make it happen. So which continuously gives you from 0 to maximum, for 0 to 360 degree, again goes back to 0. Here 0, again it goes from 0 to maximum 0, like that. So multi-turn potentiometers are also there, which can give you a sawtooth like a waveform. But that, if you can count this every time it comes to the peak, so number of times it came to the peak, if you can count, you can precisely calculate the angle that you have turned. Okay, so more than 360 degree also can be measured. Okay, so again this can be used as a graphic equalizer or audio equalizer. Position sensors as an angle sensor, controller knobs, so knobs that you see as audio mixer, same, and as a angular velocity sensor. Again I will talk about this very much in detail. If you get a voltage which is proportional to displacement, so this parameter, this particular relation can be used to measure voltage output is proportional to displacement. So rate of change of voltage is also proportional to rate of change of displacement. Got it? So this is what we will be using to find out the velocity. So this is the velocity, this is rate of change of voltage. If somehow we can measure rate of change of voltage, so we are done and we can find out the velocity also. So that is the first principle that we will be using later on. So it is, this one is used as various things which are mentioned here. So it is position sensor, controller knobs, as velocity sensor, angular velocity sensor. They are again inexpensive, very simple. Okay, but yes, this also has similar problem, that is poor life, sensitive to dust and humidity. It looks like this. In the last class also I showed you something like this, but this is different. This is a potentiometer. You can quickly identify this by counting the number of wires which are there. So you see one is for the shielding, that is system earth, and then it remains with just 3 wires. So one is ground, other one is voltage, one of them is signal. That's all. So 3 wires and done. In case of optical encoder, it was 5 wire, one is casing ground, okay, just like this, and then voltage, ground, and phase A, phase B. Sometimes index is also there. So it may have 5 or 4 wires, but this always has 3 or 4 wires because of this shielding ground. Okay, so that is there. Okay, so this is how it looks like. So they are exactly the same. Flanges are such design that you can quickly replace your optical encoders to this. So they are interchangeable. Okay, we have already used Hall sensors for BLDC motor to detect rotor position. Okay, so today we'll learn about the principle, how it works. So yes, so there are many materials which can be used like a Hall effect sensing materials. So few of them I will be mentioning here, I will discuss. Let us first understand the principle. So what it, how it is physically arranged, it's something like this. So you have a p-type semiconductor which is called as a Hall effect element. Okay, that is a Hall effect element which is here, and it is made to flow with a constant current using an external DC supply. So current continuously flows through this one. Okay, it comes out from here. So now this current continuously passes on. Then there is a orthogonal places. Okay, there are 2 other points from where you continuously measure the voltage. Hall voltage you call it here. So Hall voltage is measured. So one side of it you are entering the voltage, that is the constant supply, and then other side you are measuring the Hall voltage, that is the output voltage. Okay, so as long as there is no magnetic field, you may see a small amount of voltage fluctuations here due to surrounding magnetic environment, maybe due to some other sources. But yes, as soon as it encounters a directional magnetic field by some strong source, what do you see? You see here is a voltage. Okay, so this voltage output is proportional to the magnetic field strength that comes from this direction. Okay, so this is how it works. So yes, it is not a reed switch. There are many other magnetic switches. This is not a switch. This is a analog variation of voltage across the Hall sensor, and it is analog in nature, not like a switch on and off. Yes, mostly it is used like a switch. How? I will tell you now. Okay, so yes, it measures the magnitude of magnetic field by in terms of Hall voltage. Its output voltage is directly proportional to the magnetic field strength passing through it. So you also know magnetic field strength for a solenoid is equal to mu 0, field B is equal to mu 0, N, I and L so I, rest everything is constant, so field is proportional to current. So now you can understand, if voltage output is proportional to field and field is proportional to current, so output voltage is proportional to, let us say, if you have a wire which is at a constant distance, so that is surrounded with magnetic field all around. So yes, you can, if somehow you can link this wire's flux to this plate, in that case you can measure current flowing through this wire also. So this can be used to measure current. Okay, so if you can estimate the current of a motor, so you also know torque is proportional to current. So yes, this voltage can measure current also, it can also measure torque. So this is how it goes on. So you keep on relating things in next to next level, keeping the constant aside. So you can take this voltage output to measure torque, to measure current, to measure directly the magnetic field also. Okay, so these are few stuff that you can measure. Other things you have to make some arrangement on top of it. So how to do it, I'll just explain here. If this voltage comes here, you have a comparator which is here that can give you output. So there is a voltage level which is set here using, again, like a potentiometer we can set. Okay, so this is the voltage, this is the level with which I want to compare. So here goes your input voltage. So you can compare with this, and so as soon as it crosses some threshold level, this is an operational amplifier, I tell you. Okay, so yes, this output now will be high if it goes above this level. If it is below that, it will give you a zero signal. So using a comparator, you can trigger a voltage. Okay, you trigger like a switch. So if the voltage goes beyond certain value, it is high, less than that it is zero. So that is how it is used as a counter. Okay, let us say your rotating shaft now is fixed with a magnet and you have a Hall effect sensor which is here. So this will give you output every time this shaft crosses this plate. Okay, so this is your magnet, this is your magnet, this is your rotor. So yes, the output voltage here will have a square waveform as an output. Got it? So every time it comes near to it, gives you 1, goes to 0, gives you 1, goes to 0, and so on and so forth. So you can simply count number of square wave peaks you have seen and you can directly get the RPM value. So that is how it can measure the velocity. Okay? Okay? So this is how, combined with the threshold detection, a comparator can be used and it can trigger like a switch. Okay, so this is the way it can be used, like that. Okay, so it can be used like a proximity sensor. So anything with a magnetic element, if it comes nearby, it detects. So that is what is a proximity sensor. If it comes nearby, you detect it as high. So sometimes in case of a pneumatic cylinder also, two ends are fitted with Hall effect sensor, so that if it is fully extended, you get a signal. If it is fully retracted, you get another signal. So depending on those two signals, you come to know your status of your pneumatic cylinder. So this is how it is used, like a proximity switch. And now how the position of the shaft, that day you got using BLDC sensor, you had 3 of them fitted in the BLDC. In between the coils you had 3 of them. So based on the strengths of signal which is coming from all 3 Hall sensors, you were able to determine your rotor position. At least to some precision, to some extent you were able to get it. So this is how you can detect the position also. So Hall effect is a multi-dimensional sensor which can be used to detect proximity, position, tilt, velocity, current. Okay, so current is related to torque, so it can be used to detect torque. So once you can detect current can relate so many things, right? So this is how it is a very useful sensor. It is very simple, and because it is of non-contact in nature, so hardly anything is there to get this damaged. Okay, but there is a drawback, it has to be isolated. Okay, there should not be any external magnetic field apart from the magnetic field that you want to detect. Okay, so any external magnetic field, so you have to shield it thoroughly and leave just one window open where you are expecting your signal to get in. Okay, it can be used like a tilt sensor. Okay, so let us say you have this plate which can detect the Hall sensing voltage. Okay, and now you have a magnet, long magnet, which can pivot about this. So if this is getting tilted by certain angle, okay, and it has now oriented like this, now the field which is passing through this plate is different. So changes in the field will have changes in the Hall voltage. So now Hall voltage is now related to, it is a function of angle theta. If you can detect that function using some calibration experiment, you can use this to find tilt also. Okay, so you got the idea actually. Any change in Hall voltage due to any reason can be detected. Any environmental changes can be detected. Okay, so advantages are many. It is very, very low cost. These materials are very inexpensive, highly reliable. They don't change its property over small period of time, or maybe for years they remain like that. A high frequency of operation. With a very high frequency you can change the magnetic field, okay, and still it can detect high or low. If you are fitted with a very good high switching comparator over here, so you can do that. It can sustain harsh environment. They don't wear out because there is no contact which is there, and they are free with humidity and dust. Okay, it hardly gets affected. Okay, so that is why harsh environment, it is suitable for those environments. Only thing you have to take care is should not get into environment with other magnetic fields around. Okay, these materials are like gallium arsenide, indium arsenide, indium phosphide, indium antimonide, graphene. So these are a few materials which has this type of property to do it. Okay, so now let us discuss about velocity sensors, that is using the position sensors, the number of position sensors that we have learned so far, using a dedicated tachometer and Hall effect sensor, just we discussed just now. Okay, so let us begin again. So yes, using position sensors, when it is used with certain time bounds, it can give you velocity. So the way the output you saw just now, it came like this. So there was a resistance, slider which was there. So output was varying with displacement. So this was the displacement. So this is your applied voltage input. So output voltage was proportional to displacement. Let us say this slider is now moving with some velocity on this slider. So what will you see? You will see output displacement changes, so output voltage also changes. If somehow you can measure the output voltage changes, so if this output voltage which is changing is now also proportional to the velocity. So using this, if this output from here, if I can feed it to this one, so now this output goes here as an input to an operational amplifier here. Okay, so what this amplifier is doing, this is nothing but a differentiator circuit. Okay, whereas the output from this differentiator is, you see, is proportional to whatever comes to the input over here. So if this is your input, the input from here, okay, the whatever is the voltage, this voltage goes here. Okay, so you can directly get the rate of change of whatever is coming over here. So output, this is a voltage. So this time the output from op amp is proportional to output from rate of change of output from your potentiometer, and this is proportional to rate of change of displacement. So voltage output now after this differentiator circuit is proportional to the velocity. This is just one way of doing it in an analog way output voltage is proportional to the velocity. Using a simple potentiometer, you can estimate the velocity. But yes, potentiometers find its limited application because of its sensitive nature to humidity, dust. It is prone to noise after certain time of usage. So yes, if at all I am using an optical encoder, how to go for it? In case of optical encoder, you saw you had what is output, which is something like this from phase A, and similarly from phase B there was a shifted voltage output also. Okay, if I can measure number of peaks per unit time, so that will directly give me a sense of velocity. So number of changes in A, high pulses in A or B, any of the channel, is its velocity. Okay, so that is proportional to velocity. You have to know how much is the width per unit time which is changing depending on the resolution of your encoder, so you can get the sense of velocity. So using an analog sensor like a potentiometer, or using anything like magnetic also, magnetic encoders also give you an output as a pulses. In that case you can simply count number of pulses per unit time, that will give you sense of velocity. Okay, so these are various good ways of doing it. Moving ahead, a tachometer can be used as an angular velocity sensor also. What is a tachometer? It is nothing but a simple alternator. The voltage output from an alternator is proportional to the shaft speed. Okay, if you increase the speed, your voltage will come up. Okay, so that is proportional to the shaft speed. So that also can be used. But yes, it may be AC voltage which is coming, which is alternating in nature. So you may require a DC, AC to DC filter, and then you can use that filtered voltage as a sense to measure your input shaft velocity. Got it? So the voltage proportional this time is proportional to the rate of change of flux linkage. So that is the reason rate of change of flux linkage is again proportional to the shaft speed. Okay, so this needs a rectifier and an analog to digital converter called as ADC over here. Okay, so these are very good smart methods to do it. Yes, there are dedicated encoder interface also. You need not to count, let this device do it for you. This is the way industry works. Okay, so in industry you need reliability which is at its peak. So there are few ways, methods of doing it. Maybe if I am able to acquire this voltage signal, maybe in my own software I can take software derivative also. I can differentiate things in soft also. Okay, you can directly take in the pulses from your standard digital input channel, and you just count the number of pulses, you will get the velocity. These are few ways, but yes, in industry there are dedicated ways of doing it. So this is one of them. It is a Beckhoff incremental encoder interface EL5101. It can interface one of such encoder like optical encoder, phase A bar. So yes, in industry you have phase A, you also have A bar phase which is available. That is to increase the reliability. If one of them fails, you can always have this one as a standby. Okay, not just as an standby. If both of this are giving you same input, that means your same output, that means your device is faulty. Got it? So similarly you have B and B bar which is available. So if this is 0, this is 1, if this is 1, this is 0. If that is not happening, if simultaneously both of them are 0 or 1, that means your device is faulty. So that is also used as a fault detection. Okay. So and then you have index which comes here, C and C bar is to be fitted. Okay. So these are the connections to interface your optical encoder, and encoder supply goes from here. Okay. And then this is, so encoder supply is 0 to 5 volt range. It is only 5 volt which comes here, although you are inputting 24 volt to the system over here. Okay, because in industry 24 volt is readily available, whereas 5 volt is not available. So this device makes 5 volt available for this encoder interface. Okay, so for this encoder which takes in 5 volt only. 5-volt signal, these are all indicators which are here. Okay, so there are many other input for other diagnostic and controls. Okay, so 5 volt is generated from here. Resolution you see is very high. It can go as high as 16 or 32 bit. You can change. So why somebody should come down from higher resolution to lower? Because every time you don't need higher resolution and you want to avoid too many flooding of data, too much of data which is flooding in your system. Your values are going very high. So in that case you can switch down to 16 or sometimes even 8 bit, but this doesn't allow you going to 8 bit at least. So yes, quadrature encoder is there also. So as I have told you in last class, if you have phase A and you have phase B, so you can simply have rising edge, falling edge. So one complete cycle of phase A and phase B, there are 4 instances that you can record, and those can be further used to increase the resolution of your encoder count. Okay, so this is how it is done. And then 0 to 100% it is voltage control, that is not over here, at least in this encoder interface. Electrical isolation, it is 500 volt, relative humidity 95%, non-condensing nature is there. Okay, so these are a few ready-made available things which are there apart from standard digital input output that also can be used to interface your encoders. Okay, so but this has a quite good amount of ready-made features in it. It can directly count and give you the velocity. Okay, it can give you position, it can also give you velocity. So that is the beauty of having such interfaces. So yes, that's all for today. So in the next lecture I'll be discussing acceleration sensors, resolvers and synchro. Those are AC devices, alternating current devices, which are mostly used at the rear part of your industrial AC servo motors. So that is there. And accelerometers, which again is a special kind, that is micro electromechanical system. So we'll be discussing all of them in the next class. That's all. Thanks a lot.